Okay, this is the Math 1401 Zoom meeting for April 26, section 10.3, last section of the class. And what we're going to do here is a 4-step test of hypothesis. All right, there are no my lab problems due week. Final exam is next week. Details will be emailed out on Wednesday. Okay. Let me try to just in plain English, as much plain English as I can, just lay out exactly what these 4 steps are. You'll be given an old fact. That'll be called your null hypothesis. A new survey will be conducted. It will come out, it will have results greater, less, or different from the null hypothesis. That will nail the kind of test. It will have results either greater than, less than, or different from your null hypothesis. This will allow you to write hypotheses. Too fast. From this, you will write hypotheses. This is step 1. Step 2. You will set up the test. And find what we'll call your backwards T. Step 3, I think the book calls it this test statistic. You will compute the forwards T based on the new sample. Finally, step 4. You will compare T values. Steps 2 and 3, and draw conclusion. Remember from 10.1, there are two phrases for conclusion. You will either reject null hypothesis or you will fail to reject. All right, I realize, until you see an example, it doesn't make a whole lot of sense. So that's obviously the next step is just to walk through some of the homework problems and see if we can show you how this works. By the way, this is called the classical approach. Ignore what's called the p-value approach. We're not going to mess with p-value approach. All right. Why don't we start with the very first homework problem, which I believe was problem 13, and they kind of roughly outline the steps. There's one part we can ignore, but in the different parts, it basically roughly outlines, and there's a lot of words to these problems. Page 457, problem 13. About the ACT is a college entrance exam. I don't know if I can hold it up to the camera and have y'all read it. And it's determined that a score of 22 on the math portion of the ACT suggests the student is ready for college level math. To achieve this goal, they recommend to take a core curriculum. Y'all remember these wonderful days of your high school core curriculum, Algebra 1, Algebra 2, and Geometry. So it was a random sample of 200 students who completed this core set of courses, resulting in a mean ACT score of 22.6 with standard deviation of 3.9. These results suggest to students who complete the core curriculum are ready for college level math. That is, are they scoring above 22? Or another way of asking this is the difference between 2.6 and 22 significant. We're going to run a 4-step test of hypothesis to decide this burning question. Okay, so step 1, I'll just number the steps like this. Null hypothesis, the standard score of 22 is taken to be our assumed fact. And what we're testing again, okay, I'll just come over here to the side. Our new survey, they did a survey of 200 students, found a mean of 22.6, right? Standard deviation of 3.9, kind of mixing population and sample symbols, but it doesn't much matter. Okay, really, so it is this new mean of 22.6 significant? And does this suggest, if it is significant, then it suggests that yes, they are ready for college level math. All right, now there's no language here about being different from or anything, so the 22.6 is greater than 22. Our alternative hypothesis mean greater than 22 then. All right, now we'll go to step 2, and we're going to set up, I'm just making a few notes. You don't have to write my little notes, but I'm just trying for teaching purposes to explain what I'm doing. I'm setting up then a right tail test on this one based on that symbol. So I draw a right tail test. Remember, we hit this in 10.1 last week. Shading this in. The other number I need is the alpha value. They don't give the alpha value till part C. So I'm really, this is part A. Part A says state the appropriate null and alternative hypotheses. So instead of numbering steps 1, 2, 3, and 4, part A states your hypotheses. So I usually number them steps 1, 2, 3, and 4, calling it a 4-step test of hypotheses. Now we're ignoring B on this one. If you look at the assignment, we're not going to verify the requirements are met. Not going to mess with that. So I'm really doing part C here from the book. I'm calling it step 2, meaning use, notice it refers to a classical or p-value approach. We're going to ignore p-value. I'm doing a classical approach. All right, and one thing I do remember not mentioning in 10.1 is that the name of this region, the shaded region, is called reject region. Notice where you reject the null hypothesis. Notice that's where you're going to draw your conclusions from. The other non-shaded part is called fail to reject. You do not have to write these names, but just be aware any shaded region is called reject. Shaded. So if it's a left tail test, it's shaded over here. If it's two tail, then you got reject regions on both ends and fail to rejects in the middle. Okay, we are setting up this right tail test. Remember, the 0.05 is the area in that tail. I did mention that last week. It's also the area on a left tail. If this was a left tail, it's not, but on a different problem, it is left tail, it'd be the area in the left tail. And remember, if it's two tail, it's divided by 2. Okay, N is 200. That means my degrees of freedom is 199. I have a feeling that won't be on the table. Nope, it's not. So we're just going to have to play the game, guess what number to use. We'll use, I guess, 100 as being 200 closer to 100 is 1,000. So we got to find the 0.05 column under area in one tail. 0.05 column is second one over. And we'll use 100, 1.660. The significance of this is a t-value, the number of standard deviations to be significant. Number of standard deviations to be significant. Okay. Step 3. I call that my backwards t. Forwards t. Remember, on a forwards formula, you're going x minus mean divided by standard deviation corrected for sample size. Next page. So this is where you're bringing in your new information. 22.6. Think of it as new mean, I'll write it over here. New mean minus null hypothesis mean divided by standard deviation corrected for sample size. So I got 22.6 minus 22 divided by 3.9, which is divided by the square root of 200. Parentheses there, parentheses there. If you need to watch me punch that in, see if you get what I get. .6 minus 22. parentheses 3.6 divided by the square root 200. I think I got all the parentheses matched. I'm getting 2.3578. We're not splitting things off or anything. We'll call that 3.6 T 3.6, but we're not splitting things off or looking anything up. That's different set. This is a different animal. You just need this number. What it says is there are 2.36 standard deviations between 22.6 and 22. Is that enough to be significant? That's the purpose of step 4. When I put When I put 2.36 up here, see, it's way over here greater than 1.66, greater enough to reject the null hypothesis. So that tells you to the conclusion we're going to reject the null hypothesis. And this difference is significant. All right. So that's how you draw your conclusion at the end. Think of the old mean being at the center here. And so you're setting up, they tell you to do your level 0.05, giving you the column, your sample size giving you the row, and that gives you a t-value here. And if you wind up, when you do your new survey with a t-value over here, you're too close to the center for there to be a significant difference. But this one worked out to be a significant difference. This one with a mean of 22.6 in these numbers gave you a t of 2.36 standard deviations, throwing you way over here, very far from this. Bigger than 1.66, big enough to be significant. And that is a full 4-step test of hypothesis to decide if there is a significant difference between your new survey and your old survey, or your old number, given fact. You can see the whole thing. Okay. Let's try another one. It's once you see 3 or 4 of them, it's very repetitive. It may seem a little strange, but once you see 3 or 4, it is really repetitive. It's a matter of spotting your old fact and then writing down your new survey. Why don't we try the 15, page 457, effects of alcohol on the brain. They give you a little anatomy lesson about the brain. A study published in the American Journal of Psychiatry, researchers wanted to measure the effect of alcohol on the hippocampal region. Here's your anatomy lesson. The hippocampal region is the portion of the brain responsible for long-term memory storage in adolescence. And they want to determine the effect of alcohol. Just do adolescents who drink a lot of alcohol, do they affect that region of the brain? They randomly selected 12 adolescents with alcohol use disorders to determine whether the hippocampal volumes in the alcoholic adolescents were less than the normal volume of 9.02. So somehow they have a way of measuring that hippocampal volume, and in a normal person it's 9.02 cubic centimeters. They do their new survey, and these, let's see, there were 12 adolescents, so that's your sample size. 12 adolescents found a hippocampal volume of 8.10. So it seems to be, well, at least certainly it's lower. Whether that's significant or not, that's what we're going to find out. Standard deviation of 0.7. Conduct the appropriate test at 0.01. Level of significance. All right, let's shorten it up. Step 1, your null hypotheses, 9.02. And your 8.10 is less than 9.02, so that gives you mean less than 9.02. Remember, you never use the new number here. Use the null number in both hypotheses. All right, notice that's going to set up a left tail test. Left tail. You don't have to write all these things. There'll be 0.01 in that tail. You need a t-value here. This will be in the table. Your degrees of freedom will be 11. Degrees of freedom 11, and area in the tail 0.01. 0.01 is fourth column over. Degrees of freedom 11, 2.718. See that. On screen, 2.718, but it's of course negative because it's on the left side. Once again, that divides reject, null hypothesis, from fail to reject. See, t-values from step 3 that wind up over here are too close to the center to be significant. A t-value way over here is very far from the center, far enough to be significant. Reject. We go to step 3, and we have 8.10 minus 9.02 divided by 0.7, which is divided by the square root of 12. New minus old or standard divided by the standard deviation corrected for sample size. This will tell us if it's over here, it's significant. If here is significant, if over here, not significant. Put more gibberish down. I hope that's clear. Okay, so we're going to push this one out. .10. 7 divided by the square root 12. Negative 4.55. Hope you remember how a number line works. This is 0. You'd come to negative 2.718 before you'd come to negative 4.55. So yes, that is pretty far. 4.55 standard deviations from the center. At 8.10. That's the better way to explain it. Okay, so step 4, I will reject null hypothesis. this difference is significant. Okay. That's one I was able to squeeze on to one page. All right, I've done a right tail test. I've done a left tail test. Wonder if I should try a two tail test. Credit scores. No, I don't think 17. 19 is actually not even from this section. I remember that. 19 is actually a confidence interval problem. Hope y'all remember how to do a confidence interval. 21, it's not really clear how they want that. Same, well, let's see, 23 in rainwater have changed. Okay, 23 is a clear two-tail test. It's about calcium and precipitation in rain. So calcium is essential to tree growth. And so they measured calcium. The average was 0.11. Random sample of 10 dates gave us this data. We're going to ignore Coleman probability plot, box plot, not okay. So does the sample evidence suggest calcium concentrations have changed? Okay. Not going to be as kind to us in this. We're going to have to punch in the data and get the new mean and standard deviation. Page 458, 23. I'll give you the data 0.06, it's only 10 numbers. 0.183, 0.87, 0.20, 0.070, 234, 262, 313, 126, 108. This is the data. The old mean equal 0.11. New. Well, the n is 10 because there's 2, 4, 6, 8, 10 numbers. All right, but I need the mean, I need the standard deviation, and they're telling me the alpha is 0.05. I've got to punch in to get those. Hopefully everybody remembers how to do that. Let's see, stat, edit, 0.065, 3, 7, 0, 7, 4, 262, 3, 108. Stats, calc, one variable stats, enter. I'm getting a mean of 0.157. And you can round it a little bit. You don't have to round it exactly the same as I do. 0.087. Okay, so step one, null hypothesis then is mean equal to 0.11. Alternative, not equal to 0.11. I'm not looking at this and saying it's bigger. It says, has it changed? Does the sample evidence indicate things have changed? Have changed is different from that signal's two-tail. We will do a two-tail test. 0.05 divided by 2 is 0.025, 0.025 with 8 degrees of freedom equal 9. Degrees of freedom equal 9. Now, you can read this one. It's 2 tails, it's 0.025. Area in 2 tails, it's 0.025. Area in 1 tail, no, it's area in 1 tail is 0.025. Area in 2 tails is 0.05. But they both point to this middle column. Area in 1 tail is 0.025. The area in both tails is 0.05. With degrees of freedom 9. 2.262. 9, area in 1 tail is 0.025, area in both tails is 0.05. It's 2.262 that way, 0.262 there, failed to reject in the middle. If we get a T on either end, bigger than 2.262 standard deviations, it is significant. Reject, reject. So when we go to step 3, our T is new is 0.157 minus old is 0.11 divided by 0.087, which is divided by the square root of 10. Wait a minute, 0.087. Ooh, I'm glad I caught that. No. Okay. Okay, I have to start over. Okay. 57 minus 0.11 divided by parentheses. Standard deviation is 0.087 divided by the square root of 10. .708, we'll call it 1.71. Notice that's in the middle. In the fail to reject region, so that gives us our conclusion. Fail, reject, null hypothesis. This is not a significant difference. Okay, well, that gives you an example of each type of test, left tail, right tail, and two tail. A few more I still haven't done. Maybe we'll do one more or so. Thursday at 12, and then spend the rest of the time on the final exam review. And then whatever we don't get done, we'll finish up at 8 p.m. on Thursday with the final exam review. So I hope this helps get you started. No MyLab problems. And we will maybe see you on Thursday. Hope so. Thank you.